instance window, then go for browse option. So now we need to browse our symbol which we created for the XOR gate. So it is present in the library XOR gate, cell name XOR gate, and the VVS symbol. You close this, hide. So now you place this XOR gate symbol in your test schematic, and then press escape to remove that symbol. Okay, so now in order to verify these participants, please let me know if you are following or whether the speed is fine. If I have to slow down, you can just unmute yourself, or you can put a message in the chat box. Or if you are unable to understand anything, or if you want me to repeat anything, please let me know. Okay, so once the symbol is imported here, now you add the pin for output here by pressing P, or you can click on this create pin option. So I'm just typing the name of the output pin as V out. Click on hide and place it here. So apart from adding the output pin, I need to add the actual DC voltage source for VDD, ground connection to your VSS, and I need to apply the pulse input for your A and B. So in order to add those voltage sources, now I'm going to create instance option, then go to browse option. So your voltage sources are present in the library name called as analog lib. So click on this analog lib. You can search by typing here under the cell name. The DC voltage source name is VDC. So search for the component name VDC, and VVS symbol should be highlighted. Then close. So now once you come back from the library browser, in the add instance window, it is displaying the properties of your DC voltage here. So I'm just typing the DC voltage as 1.8. Then click on hide. I'm just, so you can press R from the keyboard to if you want to rotate the component before the placement. Then press escape. Once again, go for the add instance option. Go to browse. Now you search for V pulse, which will act as the pulse input for your A and B. So now we can see the properties for V pulse is being displayed here in the add instance window. I'll keep voltage 1 as 0, voltage 2 as 1.8. Then period for this, we'll keep it as 20N. Rise time as 10 pico, fall time as 10 pico. Then pulse width for this, I'll keep it as 12N. Then click on hide. See, how do I get different combinations of input? Now I'm placing one more for B input here. So now I can select the second component and press Q if I want to edit the properties of this. So for this one, I'll make 30 as the period and 15 nanoseconds as the pulse width. So later, if you are not getting the all the four combinations of the input, then you can change this pulse width and the period of your pulse. Now, apart from these components, I want to have the ground connection. Once again, go to this create instance, go to browse option. Under the cell name, type and search for the ground. GND is the cell name that we use for the ground. So close the library browser, click on hide. Now you place these ground terminals wherever it is required. So now use the narrow wire and complete the connections here. So the positive of this pulse is connected to B input and the positive of the second pulse is connected to the input A, and its negative terminals are connected to the ground. VSS is connected to the ground. Then positive of this DC voltage source is connected to VDD and negative is connected to the ground. Okay. So now I have completed my test schematic. See, while placing these components, you should be careful that you will not place any components inside this dotted IO boundary. Okay, any connections or any wire moving inside this uh, dotted boundary is not allowed. Then your tool will be throwing the errors. So once the schematic is completed, click on check and save. Now we'll go for simulating this. Go to launch option, select ADEL, go to setup option and check if the model libraries are set properly. So here I have the model file that is for 180 nanometer gpk.acs. Okay, this is the correct file. Then click on OK. Next, go to analysis and choose transient. First, we'll check with the transient. If it is fine, then we'll go for the other analysis. I'm keeping the stop time as 100 nano. Then accuracy defaults to moderate. Then click on OK. Then for setting the output values here, go to outputs to be plotted, select on design. You select your inputs and then the output wire. Then press escape and come back to your EDEL window. So EDE stands for analog design environment window, where we are going to set the simulation constraints. Okay, so let's run this. So how many of you think that we'll get the proper output? So one major step I have not yet done. What is that? I'm asking the question. Yeah, as some of you have correctly replied that, so we have missed out the setting of the widths for our transistors. So let's see if we have not set the widths properly, then how our output will look. So I'm just clicking on this netlist and run button here. Okay, so this is the output that we are getting. But if you want to really design it for equal to match the rise and fall delays, we need to resize your transistors. What I'll do is I'm just selecting this symbol and press Shift E. I'll descend to my schematic here. Okay, so according to the RC delay model values that we have calculated, okay, this equivalent resistance for rise and fall delay should be equal to R. Okay, so then for this inverter, so what we should do for PMOS, instead of 2, it should be 4, because so in order to have the equal resistance for your NMOS and PMOS, the width of your PMOS should be kept double the width of your NMOS. So let's see what is the width of your NMOS here. The width of the NMOS is equal to 2 micrometers. Okay, so what I have done is I have kept the PMOS width as 4 micrometer. So I'll repeat the same thing for your below inverter also. I'll make the total width of this PMOS as 4. So now what should be the sizes of this PMOSs in your XOR gate? So you can just type your answers in the chat box. Let's see how many of you will be able to answer it correctly. So here, the thing that should be taken care is we already have the NMOS width is equal to 2 micro. So Sachin has given the answer as 4 micro. Even we need to resize the sizes of your NMOS also. So only one answer, 4 micro, is the wrong answer actually. See, one thumb rule that you have to remember is whatever the standard R value that we are taking, so that is the resistance of the transistors, for the available minimum width of the transistor. Now the minimum width is already already equal to 2. If the resistance is R for width is equal to 2, so I need to change this NMOS width also to 4 here, because I have two transistors in series here. I'm keeping them as 4. So if so this is 4, then what about this PMOS? Yeah, this will become now 8. Okay, I hope that all the transistor sizes have changed. So in order to change any properties of any component that is available here, what you have to do is select the component and then press Q. Okay, so then you will be able to edit the properties of these components available here. So once you have edited this, once again go and click on check and save option. So in order to come back to your test schematic, press Ctrl E from the keyboard. Then you will come back to your test schematic. Once again, click on the check and save option to update the changes that you have done to your schematic. Now you go back to your ADL window and then. So here in the ADL window, I'll add a few more analysis here. I'll go for analysis choose. So we'll add the DC analysis for our circuit. Select save DC operating point. Then sweep variable, we'll take it as component parameter. Then click on this select component. So you select your V pulse, any one of the V pulse, and click on this DC voltage and then click on OK. Then go back to your analysis window, provide the data stop time as 1 and 1.8 and then click on OK. So now let's run this simulation. Okay, so now you can look into the output and these are the DC characteristics that I am getting for my XOR gate. Okay, now let's do the power and delay analysis for this. To not do the power and delay analysis, I am just sending here selecting the first output signal, then right click and then I am selecting send to calculator. Or else the other way, what we can do is we can go back to the ADL window, go to tools, select calculator. Now you select wave, then click on this function of panel. So here we have an option for delay. Click on delay. So signal 1, I'll go back to my output waveform and select net 1 as signal 1, then signal 2. Once again, go back to your output waveform and select V out, and this is just got paste in your signal 2. So here we have the voltage change will equal to 0.9 because the propagation delays are calculated at the 50% of the maximum values are available in the exam. So then the number of transactions, since we have two inputs here, I am going for the number of transactions as multiple. And here type 1, I will keep it as rising, and if type 2 as falling for calculating PPHL value, that is expressed now. This is for specific signal 1. Then click on apply. So you have the delay here. So you can click on send to the setting button. Green arrow is this send for expression AD also. So now you can see when you go back to your AD window out here. So you can see that expressions are here. So this expression in my mind will give as PPHL with respect to signal 1. So then I'm just exchanging this type edges as falling and then rising, and then click on apply. Again I'm sending this expression waveform or AD window. Now this expression I'm calling it as PPLH underscore with respect to signal 1. Similarly, I have performed things for signal 2. And since we remain here as net 2, or else what you have to do is place your cursor in signal 1 and go back to your waveform window and select now net 2. And copy and paste that expression into your signal 1. With respect to signal 1, I want to calculate PPHL value, and 19 pins is H type 1 as rising, H type 2 as falling. Then it's multiple, then click on apply, and then send this expression to the area window. So and then calculating the PPLH value, just exchange area types falling and rising, and then click on apply, then next send this expression to your area. Now in this case saving window. So the PP for signal 2, and this is PP H for signal 2. Okay. Now one transition. So now here we have got the delays here. Okay. So now how do I come to know what is the propagation delay here? Here out of this PPHL with respect to signal 1 and signal 2, we have to know which one is having the maximum value. So let's calculate the maximum value of this. I'm just going for the option Y max for this TPHL underscore signal 1, and I'll add this expression to my ADA window. And then I'm selecting TPHL value for signal 2. Once again, send this to calculator. I want to know what's the Y max for this. And again, I'm sending back here. I'll go back to my ADL window and rename them. Or else it is fine that we are able to make a Y max for TPHL signal 1 and TPHL signal 2. Then I'll go for TPLH values, finding what is the maximum TPLH I'm getting. Now let's go back to our ADL window. Okay, now to get this values, just click on run button. So I'm just waiting for the simulation to complete. Okay, so now let's go back to our ADL window. Now here you will be able to observe here. See, out of both the signals we have TPHL and okay, almost the TPHL is same for both. But when it comes to the TPLH value, I have here 69.54. Okay, now we need to calculate the average of this TPHL, which is having the, okay, either you can take signal 1 or signal 2, since both are same actually. So usually sometimes they may have the different values. Okay, then at that time, whichever the signal has the maximum delay, then we need to consider that. Okay. So now it will be the total propagation delay will be equal to 15 plus 69, 15 nano plus 69 pico divided by 2. So this will give you the actual propagation delay. Now let's go and calculate the power for this. So in order to calculate the power, go to outputs, then click on save all, then click on all option, then click on OK. So once you have saved the outputs, then click on run simulation once again. So in order to get the power plots, go to tools, so go to results, direct plot, main form. So for transient or for dynamic, getting the dynamic power, you can go for analysis type as transient and select power, select total power. You can keep it as add to outputs. Then click on the new window or new sub window as the option. Then click on plot. So here you can see, so this is the power waveform. So then once again, you can go back to your direct plot, select DC. So this will give you the static power of your XOR gate. Then click on plot. So this is the static power, which we have about 788.6198 microwatts is the maximum static power that we have for our XOR gate. So now this is about the analysis of your XOR gate. So if you want to retain this for further use, you can go to this session and save state. Then select cell view and then click on OK here. Then we'll go for closing this ADL window. So now we'll move on to the layout part. So for layout, we need to again open this XOR gate, the first schematic that we have drawn. So now you go to the option launch, then select layout Excel. So since we are creating it as new, then click on OK here. Click on OK. So this is our layout window. So in order to import the components into this layout window, go to the connectivity option, generate all from source. So I'm going to generate instances IO pins PR boundary. So you can minimum spacing between each component. I'm just keeping it as 0.3 here. Then if you want to place all the components inside the boundary, then select in boundary. Then preserve user defined bindings is enabled. Then click on OK. See now, here we can see that we have uneven sized NMOS and PMOS transistors. Okay. So if we have this, then we cannot have the uniform size of the layout and have the optimized layout for our design. Okay. So then how do you overcome this problem? So now if I start placing these components like this, okay, then there will be some space that will be left out here. If I don't want to waste that, this is simple example I'm taking, but see if you have unsized transistors like this, okay, even here also you can see this one is having the size of 2 micro, whereas this all we have kept it as 4 micros. Again, when you try placing this, again we have the wastage of the spaces here. See, one way to overcome this is, I'll go back to my schematic here. See, well, the minimum PMOS size that is available here is 4 micrometers. Okay. So what I'll do is all my PMOS transistors, I'll select here, I'll convert them into fingers. I'll have 2 fingers for them, and each finger width I'll keep it as 4, so that we'll have the total width of the PMOS will be equal to 8 micrometers. Okay, so I'll just change this for all, and let's see what happens at the layout. See, especially when we are going for designing any logic gates, which will actually will be converted into the standard cells. Then for any standard cells, the height will be fixed. That means that you cannot have the transistors of any height that you want. So here for NMOS, I am using again the finger of 2, but the width of each finger will be 2 micrometers. So therefore, total will become 4 micrometers. Okay, so now it is done. I'm just clicking on check and save. Let's go back to our layout window. I'll once again import my design. So going to connectivity, generate from all from source. So now you can see here, see all my transistor sizes are matching here. Okay, so I can have the uniform placement of the transistors and do the routing accordingly. So few more things. I'll just go back. I'll set. See if I come back to my layout here, and I'm unable to see the bulk connections. Okay, so I'll add those bulk connections in the from the layout itself. Just go to the properties. So here you can see gate connection also you can keep. For PMOSs, it will be at the bottom, and body type you can make it as detached and top tap. So here itself in the schematic, I'm setting everything so that it will help me ease my routing and placement easy in the layout. See, for all my PMOS, I'm keeping the gate connection at the bottom and body type as detached, and it is at the top tab. Okay. For NMOS, I'll place the gate connection at the top. As of now, I'll keep the body connection as none, but I'll keep only the gate connections as top. I'll tell you that also why I'm not adding the bulk connection or body tie connection for my NMOSs here. So for gate connections, I'm just keeping for this as top because this will be placed at the bottom side. Okay. So I can perform the same thing for, it's not required for this these inverters. That's fine, I think. Okay, checks and save. Now let's go back to our layout. I'll once again re-import my design, connectivity, generate all from source. See now, since I have made the fingers, so I'll go for the chain option. Okay, that means if there are any overlapping drains, drain and drain connections, okay, it will be automatically done by the tool and it will import the design. I'm enabling the chain option, then click on OK here. So now you can see here how your design got imported here. So I'll just keep enough space between uh, this NMOS and PMOS so that we can have the routing properly. Without any DRC violations. Okay. See now, if I just run the DRC, I'll get one error here with respect to that. See, this NMOS is this PMOS are belonging to your inverters. Okay, but it is not a integral part of this XOR gate. Okay, so I may get that the spacing error between these two N wells. Let's see if I can draw. Sure. First, we need to set the technology for verifying the DRC. Foundry analog 180 nanometer Assura Tech. So now I'm going for run DRC after setting the technology file. So I can just to separately keep all the data related to verification. I'm just going back to my directory and creating a folder called as verify. Now I'll come back and run directory. I'm just browsing my verify folder here. Then technology is selected as GPDK 180 and then click on OK to run your DRC check. I know I'll have the few of the DRC errors, but my main concern is whether I do you have any DRC during the placement. So as of now, so NWell stamp error is that is fine because still we are not connected. Okay, substrate connection is not for there for that PMOS. Yeah, this is all fine. See now, suppose see have drawn this N well completely, including all the PMOSs available here. If I delete this and once again save the design and run the DRC, yeah, see now you are able to see N well to N well spacing must be greater than or equal to 1 micrometer. Okay, so in order to one way to avoid this is just enclose this all the PMOS in a single N well. Okay, so then I'll just have the alignment here. Meanwhile, if you don't want to alter the connections, I mean the wiring of the PR boundary, then you can make it as left click inside this PR boundary and select the option make PR boundary non-selectable. Now you will not be able to select PR boundary, so that your PR boundary is fixed now. So let's just go for the routing here. So here I have the misalignment of the gate. So either I'll just move this PMOS a bit away here. And once again using the move option here, just selecting this, and M is the move option here. I'll just align these gates properly. Okay, done. So next I'm connecting the second gate. So these are the inverters that we had in our design. I'm just completing these connections. And here we have the drain. So let's check while we have done these connections. Have we got any BRC errors? Okay, so these are all fine. We'll get as we complete the connections. So minimum spacing should be maintained between your metal 1 and metal 1. So I have done these connections like this. So now we will have the pin placement. So you can go to the place option, pin placement, VDD. So I'm placing it at the top, apply, and create the H rail for that. VSS, bottom, apply, H rail, then apply, then close this. So you can see the VDD and VSS automatically will get placed here. So I need to place the N well body connection here. For that, I am just going to the create via option. Go to create via. You can do this M1L N well, then hide. So you just place this. Then press escape. So now here it is very easy to identify the connections here. Wherever we have VDD, you can just connect it. First thing is I am just interconnecting all these body connections so that finally I can have one connection that will be connected to the VDD here. This is again the VDD. So here I have net 1 and here is one more net 1 here, net 1 here, net 1 here and net 1. So all these net 1s should be shorted. So what I'll do is I'll take the metal one and right click on this and we'll select this via up to metal 2 and I'm placing this via here. Okay, then have the connection with net 1. Then next connection I want to do it with metal 2, so I am selecting this metal 2 here. So again where we have the net 1, so I'm just once again taking the wire down to metal 1 and completing the connection there. Okay, then we have V out, which should be again interconnected here. So once again, I'm taking via up to metal 2. So make sure while placing this metal 3 also you have sufficient gap in between. I'm just going to create via M1 to M2 to M1 height. So wherever you require this vias, you can just place it here. So this is V out again. So these two has to be shorted now. So then finally this will go and connect to your V out pin. So similarly, we'll also have the connections here. So this is to be connected to your VSS. So then we have the net 2 connections here. For that, again, I will take the via, go to create via. So it will be from metal 2 to metal 1. So wherever we have the net 2 connection, I'm just placing these wires there. Then I'll just draw the metal 2 wire to connect all these wires. Apart from this, we have net 3. Yeah, net 3 also. So okay. So after placing these wires, again take the wire. So this time I have to go for metal 2. Net 3 connection is done. Then from net 2, so all the wires that I have placed on net 2, so I'm connecting them. Apart from this, we have the V out also. So once again, I'll go for via metal 2 to metal 1. I'll place this on wherever we have the V out connections. Yeah. So then I'll take the wire and connect these two V outs. So then further, this V out will go and connect to your V out pin. So let's see. Meanwhile, we have done any DRC errors so that it will be easy for us to debug. Yes. Okay. Now let's click on yes here. So still we have the NVEL stamp error, piece of stamp float error. Let's see. Okay. Then I have the pin B coming over here and just take it. Then we have this VSS connection to be completed. See, we need to add the substrate connection here. So again, I'm going for the via here. So here I'm selecting M1 P sub. So I'll just place that here. So if we have got like any multi-stamp errors P sub, then we may have to remove any one of these substrates. So let's check that after we complete all the connections. So right now the pins are connected to the respective gate inputs. Now I have to complete this connection here. So I'll take the wire from metal 2 to metal 1 here. So let's draw these lines by using metal 2. So whenever if you cannot overlap the same metal layers, okay, then it will automatically make the connections. So I'm using metal 2 here to run my connections over this metal 1. This is B bar. Now this A connections we have to do. This B is already done, so we are only left with connection of A. So let's check if we have further any PRC errors. So one error I think I will get, because while moving, we have moved here and we have got some improper placement here. Other than that, if there are any errors, we'll rectify it. Okay, so as I told that only this particular point we have an issue. If I want to rectify it again, it will take more time, because all these connections has to be removed and we need to align them. I'll just show you the completed layout here. Just a minute, I'm just showing you the RC extraction part. Okay, at this point, we had while moving, we may have moved something, and we had kind of oxide overlapping error. So now we'll run the DRC. Okay. So let's go for the LVS. For LVS, you need to go to Ashura and select Run LVS. Are leaving already. 22, they become the 40 or 15. Here, the run name we are given it as LVS and technologies GPDK 180. So meanwhile, there are few questions. The chat box will try to answer them. So this is LVS is done now. So now once LVS is clear, it shows that schematic and layout match. Now we'll go for the RC extraction. Go to Ashura and select Run Quantus. So here, so since it is 180 nanometer technology, rule set will be default. So output we have to take it as extracted view. Then extraction we need to give the reference node as VSS. Then extraction type should be RC. Then disable this HRCX option. Then here the capacitor models and the resistor models should be do not include. These are the settings that we need to perform for the parasitic extraction. So what is HTrail? See, earlier by Anuraj Karan, so there is a question, what is HTrail? Here we have got a metal layer for your VDD pin. Okay, so that's what is your horizontal rail, we call it as. Other than this, so is there any quiz on the session? No, as of now, we don't have any quiz session on this. And some people are asking for the certification. Uh, it is there is no certificate that will be given for this University Tech Bytes because it is mainly meant for uh, the faculties to learn their lab experiments well and the students. So now my RC extraction is done. So I have to go back to my library manager. So here I have got one more view, that is AV extracted. So you can see this is how the AV extracted will look. So if I just zoom in here, I can find the capacitors and the resistors here. Okay. Now let's run the back annotation and check what will happen to our delays. So I'll go to File, New, Cell View, make it as Config View. In the top cell, the view should be kept as schematic. Then for global bindings, use the Use Template option. Then select Spec Tray. Then click on OK. Go to Tree View, select the folder icon, right click, and then select Set Instance View as AV extracted. Then save this, then click on Open. So now, earlier when we descended, we had this schematic view. Now if we descend into this, inside this black box, I have the RC extracted view here. Okay, now my simulation will be run with respect to this. So let's run the simulation, go to launch ADEL. Since I have saved my previous settings, I'll just go and load the settings, go to session, load state, cell view, then click on OK. Now you run the simulation. Now the values will get updated with respect to. You can come back to your ADL window. Okay. Now we have the updated values of your delay. Okay, and so we have few questions here. The one question was like, why is the delay negative? So the delay value, you'll get it as negative if like your transistor sizing what was not proper, or if the other signal is reaching faster than your input signal. If your input signal is reaching faster than your output signal, okay, then you will have the negative delay. So in order to overcome this negative delay, again you need to look into your transistor sizings. So if you have any other question, queries, we are open to your queries. So you can just unmute yourself. Or you can just type your queries in the chat box.
Hello, sir.
Yeah, yes, ma'am.
Sir, I have a question related to this Cadence online support system.
Yeah.
I have seen Cadence badge. Uh,
Yes,
so,
ma'am.
Regarding that, I wanted to ask, like we have to attend the course, and after that, is there any exam will be there for achieving
Yeah,
that?
yes, ma'am. You'll have the exam. I mean, online only. There only. It's in the course itself. That exam option will also be available.
Okay,
So there, if you click on, then you can take up the exam. Then they'll provide you. If you pass that, then they'll give you the digital badge to you.
okay, okay. Thank you,
Yeah.
sir.
Yeah. So further, any queries you have? So please stay tuned to our University Tech Bytes. We'll be coming up with more challenging experiments in the coming days. I hope that you all had a great learning today. So please do provide your feedbacks in the feedback link shared in the chat box. So thank you all for your precious time with us. So you can write if you have any queries about the cadence relate supported or Unicid Tech Bytes, you can mail to us at cadence.support@ntpal.com. Thank you all.